Hey guys, welcome back to my channel, and in today's video we are going to study the fundamental of retrieval-augmented generation. In this, we are going to study about one of the most important concepts called as vector databases. Vector databases are the special databases which stores any kind of data in form of embeddings for efficient storage and retrieval. This is the quality that makes vector databases different from traditional databases. In this video, we will study how these vector databases are different and why they are efficiently used in our RAG application. Let's say we have some kind of data. Maybe it's an image, a text, and an audio waveform. All these are different forms of data. These datasets are converted into some kind of vectors which we call as embedding vectors. And these embedding vectors are stored in a certain databases which is called as vector databases. These vector databases are not only efficient in storing the vectors but also helps in querying results by using a concept called similarity. Let's see how everything works. This is an overview of how the data is stored and how it is retrieved. Let's say we have certain kind of application. This application wants to store the data into vector databases, and at the same time when it requires, it wants to retrieve some kind of data using a query. We have our dataset. These are passed to the embedding models. These embedding models are certain specialized models of machine learning, and these models helps in converting our data into some kind of mathematical representation called as vectors. These vectors are finally then stored into our vector databases. Now let's say application want to retrieve. So we have a query. A query over here is our input data. Let's say it is some kind of input text. This text is passed through our same embedding model which was used to generate the embeddings which was stored into vector database. This embedding model converts the query into something called as query embedding. The query embeddings are then matched with the values or the vectors that are present in the vector databases using some kind of similarity matrix called cosine or maybe distance, which is called as Euclidean matrix, and other form of similarity matrices. Once the query embeddings are matched with the vector databases values, we get a similar vectors, and these vectors are then queried and processed and then sent back to the application. This is how the whole flow works, how the vectors are stored into vector databases, and how the values are retrieved when a query comes in. All these things of storage and retrieval are done through our APIs. We have store API, retrieve API, update, delete, and search. Store, retrieve, update, and delete goes from the application to the storage layer. Meanwhile, the search can go to the storage layer and then it is passed back to the application. Store, retrieve, update, and delete. All these APIs pass the data certain layer called as indexing layer. In this layer, indexing of the data is done for the faster retrieval and search. Once the data is passed through indexing layer, the data is indexed and then it is stored in a storage layer. Meanwhile, when we want to search something, the API exposes the data to query processing layer where the queries are processed, converted into embedding, and then again passes to the indexing data layer and then storage and then retrieve that. One of the most important thing that you would see in this is our indexing data block. These indexing data blocks are enabled by certain kind of algorithms which are used to index the data stored in the vector databases. The indexing layer basically indexes the data using some kind of algorithms, namely inverted file index, HNSW, hierarchical, navigable small word graph. There are tree-based methods, there are hashing techniques, and a graph-based structure. We are going to study specifically about HNSW in this video. So how these results are generated? Basically, when a query comes in, we need to retrieve a similar or an approximately similar vectors that are stored in our databases. In order to retrieve these similar vectors, we use some kind of similarity matrix. There are three kind of metrics that are basically used for retrieving the similar vectors. First one is Euclidean, which is directly a distance-based similarity matrix. This is the distance between the two vectors. Let's say we have vector u and a vector v. The distance between these two is our Euclidean distance. And this is the mathematical formulation for the Euclidean distance. Next one is cosine. Cosine is a similarity matrix which is basically calculated by this formula. It tells the angle between the two vectors u and v. How much is the angle? The lower the angle, higher is the value, and thus we have a better similarity score. The third one is our dot product. Dot product basically tells the projection of vector u in the direction of the vector v. So how much is the projection of the one vector in other vector in the direction of other vector is our dot product. This basically gives us the similarity between two vectors u and v, and the mathematical formulation for these two is this. Now how are these embeddings generated? Everything is working on the vectors. These vectors are called as embedding vectors. Here are some kind of techniques and the methodologies that basically helps in creating the embeddings. If you go into my channel, I have created very detailed video for natural language processing where I have talked about embedding techniques and the ML models and the deep learning models that helps in generated embeddings. And there is also separate video on evolution of embeddings, which is going to enhance your knowledge for this. Let's see. For the text embeddings, it is part of NLP models. For the image embeddings, there are computer vision models. For the video embeddings, there are 3D computer vision models. For the audio embeddings, we need to have spectrograms or maybe frequency chart. And then after all these things, there is something called as multimodal embeddings. Multimodal embeddings are the embeddings which are generated using the mixed data. Let's say the input data is text plus image. Many of you attach an image in the chat GPT and provide a text to convert this image into certain kind of another image. In this, we have both text and the image. This is called as mixed type of data, and the model that generates the embedding using the mixed type of data is called as multimodal. So all these are different categories of embeddings, and there are different sectors of the models which are basically helpful in generating the embedding vectors. So why can't we use the traditional databases to store the vectors? Basically, there are two concepts, data structure and an indexing. If you have seen the functionality till now, everything is working on the basis of high dimensionality vectors, which we call as embeddings. Vector databases are designed to store these high dimensionality vectors. Meanwhile, traditional databases stores data in the form of rows and columns, and the data is categorical or numerical data. Vector databases use advanced indexing techniques such as an HNSW, IVF, product quantization. These are basically helpful in getting the approximately nearest embedding vector when a query comes in. Meanwhile, the traditional databases use indexing like B-tree, and these indexing are used for the exact lookup, but are not efficient for the similarity search in the high dimensional spaces. There is something very important called querying also, which we have seen up till now. And vector databases are designed to query the data based on similarity search using the distance matrix. So to query the approximately nearest vectors, we use similarity search, which is not possible or maybe possible with very low efficiency in our traditional databases. There are certain open source vector databases. First one is Chroma DB, second one is FAISS, then we have Qdrant, and we have Milvus. Each database has its own pros and cons, but are all helpful in building a RAG-based system. So Chroma DB has some kind of pros, which has easy integration, it has document and embedding storage, it is fast and accurate approximate nearest neighbor search. When we go with the FAISS, it is similarity search and clustering of dense embeddings. It is optimized for efficient search. It uses basically in-memory indexing, which helps in extremely fast retrieval. So there are all these pros and cons for each. You can look up on their websites. Links of these websites will be provided in the description. Now let's look at how indexing works. In the traditional databases or in some kind of notebooks, indexing for certain text can be done like this. This word sahi would have occurred on the pages 1, 4, 10 and 100. Meanwhile, padhai would have occurred on pages 8, 10, 14 and 25. That means this text need not to search throughout the whole book, rather we can just go to these pages, we can find it. Similarly, in the indexing concept of the databases, these are replaced by the rows. Instead of going through all the million number of rows, we can just go through these rows and find where and what kind of data do we need. This is how we use the indexing for the faster retrieval in the traditional databases for the exact lookup. In order to build all these indexes, we use B trees and hash tables. Now what happens in vector databases? Usually, let's say we have incoming vector. This is our vectors. All these points represent vectors in a very high dimensional space. So we have very large pool of embeddings. In order to search from this complete large pool of embeddings, there is specialized indexing technique, and these can be done by HNSW and KD tree. We are going to study HNSW indexing technique and the searching process done in this in order to see how these things work in vector databases. Let's go through HNSW. HNSW is basically built on Navigable small word graph plus skip list. Let's see what is small word phenomena. This phenomena tells us that most of the nodes can be reached by any other nodes through small number of intermediate connection in the large networks. That is, most of the nodes that are present can be reached through very less number of intermediate steps. If one has to reach from this to this, it needs only 2 to 3 steps. This is called a small word phenomena. And this became popular by something called a 6 degree of separation. What does the 6 degree of separation says? It is basically a concept in network theories. It says 2 points P1 and P2 in our word network will be apart on an average with only 6 connections. No matter in which part of the world they are living, on an average, people can reach from one connection to another connection using only 6 steps. This is called a 6 degree of separation. Now the real world network. The real world network basically has two important phenomena called as high clustering coefficient and the short average path length. By high clustering coefficient, we mean the points that are together are highly dense. Meanwhile, the average path length between one point to other point is very small. Let's say a person has to reach from here to here. In order to reach from here to here, the average path length will be pretty less because all these points are dense and clustered together, and one would reach from here to here in just 6 connections. So that is the property of the real world network. Now let's move ahead. How does ANN search works? ANN is approximate nearest neighbor search. Let's say we have an input vector I. We need to find some kind of point which is approximately closer to this vector. We start from certain point and then we move ahead. Let's say our point is located over here. We start from this point and then we move. We move from here to here, here to here, here to here, and here to here. And let's say this is the point which is closest to our query point, and this becomes our top closest point. This movement is done based on the distance. This distance, and because of this distance calculation, this phenomena, this algorithm is called as approximate nearest neighbor because we are calculating the approximately closest point instead of having the exact matching point. Let's see what is skip list. Skip list. So skip list is basically combination of multi-level linked list, and all these linked lists are sorted. The lowest level linked list contains all the numbers. If we say there are only these numbers that are present in a list, the lowest level contains all these numbers. Now these numbers are promoted to the higher level based on the probability value. Let's say a probability whether the 8 will go above or not is 0.5. So every 1 out of 2 chance we will push this point to above linked list. This is how we calculate the skip list. So skip list is a multi-level linked list where the lowest level contains all the points and the levels above contains some of the lesser points which will help us to move faster. Let us understand by example. We need to find 7 in this linked list. In order to find the 7 in the linked list, we start from over here. Since 7 is greater than 5, this means we can move in this list to in horizontal direction because all this list contains a value in a sorted order. Now 7 is greater than 5. We check whether the 7 is less than 5 dot next. If 7 is less than 5 dot next, then it means we need to go to the lower level. So we transcend to lower level. Similar operation is done in this level also. Here 7 is greater than 5, but 7 is less than 5 dot next, which is 8. Now we transcend to another lower level. Now here 7 is greater than 5. We move next. We see that 7 is equal to 7. And this is the node where we find our element. It has become an exact match. And we are going to return this value. This is how skip list search work, and this is the data structure that is used in HNSW. Inspired by this, HNSW graph is developed. We have top layer and then some middle layers and then the lowest layer. This lowest layer contains all the nodes, meanwhile the topmost layer contains very fewer nodes. Let's say this is our point which needs to be searched. So we start from the topmost layer and we start from a certain input point. Since this contains a very lesser points, we are going to move faster in the top layer. We will start from here and the distance is pretty much, so we move over here. After moving from this, we'll move to the lower level. Once we move to the lower level, we see that with this point, we move over here. Now once we move over here, we can either move in this direction or we can move to the downward direction also. If we choose to move in this direction, we are going to find the point over here. But for the sake of completeness of this example, I have moved to the lower level also. We move to the lower level also, we are going to see that this is the point which is very close to our target point. And thus, we are going to return this node. This is how HNSW work. And this is how we search and retrieve the points. Now there is one more important concept in vectordb, which we call as data compression and dimensionality reduction. Both of these are important because there are certain problems that are associated with the high dimensional data. These challenges include storage cost, query performance, high computation, curse of dimensionality, very famous concept and very important concept in machine learning, overfitting, scalability. All these issues arise because the data is very high dimensional. In order to solve this problem, we go to the data compression technique and the dimensionality reduction techniques. The dimensionality reduction techniques contains algorithms like PCA, TSNE, etc. We are not going to talk about these things because these are the concepts related to machine learning algorithms. There is certain called data compression techniques. One of the most important data compression technique is called as JPEG, PNG, etc. And in our case, we are going to study PQ called as product quantization. Let's see how the product quantization work. We have a very high dimensional input vector. We have very high dimensional vector. This vector is divided into subvectors. Each subvectors are represented by a certain form of code, and these representative points are called as centroid. Basically, each subvectors are clustered through certain kind of clustering algorithms, maybe k-means. When this k-means algorithm works on these subvectors, we generate centroid. These centroids are present in our codebook. And basically these centroids are the representation of our subvectors instead of using the big dimensional vectors. Let's see with an example. We have v1, v2, v3 and vn. All these are subvectors. Now once the clustering algorithm is run over all these subvectors, we get the centroids for each subvectors. Let's say for v1 we get c1, v2 we get c2, v3 we again get c1 because the codebook is shared across all the vector spaces. And then we have cn. What happens? These centroids are given in integers. We have 0, we have 1, we have 0, we have k. Now in order to represent these subvectors, we will represent it as vector of 0, 1, 0 and k. This is how we have come from this much of dimension to this dimension. And we have done our data compression technique. What happens when a new query comes in? When a new query comes in, similar process is repeated. We split into subvectors, we calculate the distance with the centroids. We calculate the distance with the centroids of these vectors from a pre-computed table. Once the distances are calculated, we sum up the distance, and that is the distance which is approximate distance from the stored codes. So when a query vector comes in, what is the distance from these representative code is calculated through this mechanism. This was all the important concept of the vector databases. This is one of the most important concept that is used in RAG, and it is asked in many interview questions because in the RAG pipeline, it is very easy to just plug in a large language model, but many of the people are missing the technical concept of storage and retrieval, which is done through vector databases. I hope you all would have liked the video. Please share and subscribe. Thank you for watching.